Today we're going to summarize methods for preventing or mitigating ASR-induced damage, including talking about specifications to ensure that this is managed. Next week we'll be providing case studies of ASR-affected concrete structures, including rehabilitation strategies. Overall, there's been 8 different presentations, well, 7 really, apart from the initial introduction. Last week we dealt with fundamentals of AAR, symptoms, and the different test methods. Today, as we mentioned, we're dealing with prevention and specifications, and next week we'll be dealing with diagnosis and prognosis of ASR and for repair methods. So next week is very much about what can I do if I've already got ASR, whereas today is all about trying to prevent it in the first place. Just a reminder from last week, we learned that the 3 things that are required to induce ASR or alkali, to induce ASR are reactive silica, alkali, and moisture. And if we can try to eliminate or at least control the concentration of one of these 3 things, we can have some opportunity to control alkali-silica reaction. Recognizing that it's difficult to control moisture unless you have to, unless that's your only option, which is often the case when you're dealing with existing structures that have ASR. For new construction, we would prefer the choice of either limiting the amount of reactive silica in our concrete or limiting the amount of alkali. So when we look at our preventive measures for alkali-silica reaction, they fall into sort of broad categories. The first and perhaps the most obvious choice is to use non-reactive aggregate. In other words, that would be aggregate that didn't contain a sufficient amount of reactive silica to make it deleteriously reactive. Numbers 2 and 3 kind of combine. They're both to control the alkali content of the concrete. If we can limit the alkali content in the concrete by the use of low alkali cement and other means, then that gives us another opportunity to control alkali-silica reaction. The 4th bullet there is to use supplementary cementing materials, which indirectly is also a way of limiting the alkali content of the concrete. As we'll see, SCMs work by basically consuming alkalis before they can attack the aggregates. Finally, the last bullet on there doesn't really fit with any of the sort of 3 points in our triangle. This is the use of suitable chemical admixtures, and we're talking specifically about the use of lithium-based admixtures. Lithium doesn't reduce the amount of available alkalis or change the amount of reactive silica, but it changes the nature of the reaction. And we'll discuss that fairly briefly towards the end of this session. Using a non-reactive aggregate is our first option, not necessarily our preferred option, but the most obvious perhaps. And there are 1 or 2 problems associated with doing this. One is that by using a non-reactive with active aggregate, we're really relying on our test methods to be reliable in telling us that our aggregate is non-reactive. And one of the structures that kept popping up last week as an example of ASR was this dam here, the Mactaquac Dam in New Brunswick, Canada, which is only about 15 miles away from me as I sit here in my office. The aggregate that was used for this structure did in fact pass the current tests that were in vogue at the time, which was ASTM C227 and also ASTM C289, if people are familiar with their test methods. And the aggregate actually passed both tests and was declared as being non-reactive. Here we are about 60 years later, and the dam has actually grown in height by 7 inches already, and it really is a very severe case of alkali-silica reaction. So that's one problem associated with this option is our aggregate is only as non-reactive as our tests tell us it is, and we're relying very much on the test methods in this sense. In addition to tests identifying the aggregate as being non-reactive, another problem is, of course, that we may find ourselves in geographic locations where the sources of non-reactive aggregates may be scarce, possibly even non-existent. And in such cases, we may really need to consider marginally or reactive aggregates that otherwise behave well in concrete. And we may need to look towards other preventive measures to allow us to use these aggregates safely. Magnetic dam, again, sorry to return to the structure, but this is a situation where this occurs. This dam is going to be replaced in about 20 years from now. And when they replace this structure, they're almost certainly going to have to consider very seriously using the exact same aggregate that they used to construct the dam. The reason for this is the excavation for the dam is going to result in the production of millions of tons of aggregate that, aside from being ASR, are otherwise usable as concrete aggregates. There's going to be somewhere in the region of 500,000 cubic yards of concrete required for this replacement. And if they can actually use the aggregate that's actually there on location, economy really dictates that they should. So they're looking very seriously at reusing this aggregate and taking other preventive measures to avoid the same problems from occurring. So if we don't have reactive aggregates economically available to us, our second option is to perhaps control the alkali content of the concrete. And for a long time, it's been known that using low alkali cement can reduce the risk of alkali-silica reaction. In some specifications, there's almost complete reliance on this. Unfortunately, using low alkali cement doesn't eliminate the possibility of ASR, it merely reduces the risk. The use of low alkali cement was first proposed in the very first paper that was written on alkali-silica reaction by Thomas Stanton in 1940. He conducted experiments with his reactive aggregate, and he combined this with 7 different cements that were available in California at the time. And he ran this concrete mortar bar test that you can see here on the left. This was another one of Stanton's inventions, if you like, discoveries that you could store mortar bars over water and induce expansion due to ASR. He ran this test out for 2 years with 7 different cements, and he found that when the cement alkalis were somewhere above 0.6, he got expansion, and when they were below 0.6, he got no expansion. And this was really the sort of birth of the concept of low alkali cement. And that 0.6% has stuck with us for many, many decades since as being the sort of demarcation between low and high alkali cement. We have known for quite some time that low alkali cement is not sufficient on its own as a prevention. It doesn't provide a 100% guarantee that you're not going to get an alkali-silica reaction. And there have been cases reported in the literature, more than just this one here, but this is perhaps one of the more well-known cases, where concrete has exhibited severe ASR-related damage with cements that have alkali content significantly below 0.6%. Part of the reason for this is that it is possible with a low alkali cement to still achieve a relatively high alkali content in the concrete if you have a very high cement content. This is a slide that I'm re-showing from last week, and it basically shows for a specific aggregate that expansion here on the y-axis is a function of the actual alkali content in the concrete rather than the alkali content in the cement. These are all different concretes produced with different alkali contents, different cement contents, and different cement alkalis. And you can see that really the amount of expansion is quite closely related to how much alkali is in the concrete. So our preferred approach, rather than just using the cement alkalis as a sort of indication of risk, is to use the concrete alkali content. And the concrete alkali content is basically the product of the cement content and the alkali content. So if we multiply our cement content by our cement alkalis, divide by 100 because our cement alkalis are expressed as a percentage, we'll get the concrete alkali content. And here's an example down here. That this should say pounds per cubic yard here. If we had 600 pounds per cubic yard of cement with an alkali content of 0.78%, and we can multiply these together, and this gives us our actual alkali content in the concrete. In this case here, just slightly under 4 pounds per cubic yard. There's a lot of work in the literature that will show us that the expansion for given aggregates can be related to the alkali content of the concrete, just like this graph shows here, where we get we're below a certain threshold, which for this aggregate is 5 pounds per cubic yard or 3 kilograms per cubic meter. If we're below this threshold, we get very little expansion, no significant or damaging expansion, and as we increase the alkali content above this level, we get an increasing amount of expansion. Every aggregate would be expected to have a different threshold content for expansion. This one here is shown to be about 5 pounds. For some reason, I'm having trouble moving on. Oh, there we go. Based on relationships like this, for a number of years, starting in about the 1980s and including the 1990s, a number of specifications actually use limits like 5 pounds or 3 kilograms as a means for controlling ASR based on laboratory testing. However, we've since learned that expansion can occur at lower alkali contents in the field than occur in the lab. For instance, if we were looking at the relationship to this aggregate in the field, we might find that our S-shaped curve looks something like this. We'd actually get expansion at lower alkali content. Okay, so 5 pounds per cubic yard seems to be the sort of limit that we might see from a laboratory, but as I said, there is evidence that we can get expansion at lower alkali contents in the field, and I just thought I'd show you a few examples of this here. Here we have a structure where the alkali content is significantly less than 5 pounds per cubic yard. You'll have to excuse me, for some reason my computer is lagging here. And we have another couple of structures where the alkali content is somewhat less than 3.5 pounds per cubic yard. So we have learned a lesson over the time that the alkali content required in the field is less than that required in the laboratory in terms of producing expansion. I think for those of you who attended last week, and hopefully most of you did, one of the things we learned last week is that our current test methods that we're relying upon, like the concrete prism test here and the accelerated mortar bar test here, are not really effective means for establishing what the minimum level of alkali is that's required to establish ASR with a given aggregate. The most reliable way for doing this is to actually cast concrete blocks at different alkali contents and determine what the threshold level is. Unfortunately, of course, it isn't very practical to do this under most circumstances. We really have learned that the size of specimens does matter. Here's some data from one of my own studies using a reactive flint aggregate. See here's a block expanding here because of alkali silica reaction. If we ran this test, if we tested this aggregate at a series of alkali contents, which are shown down here on the horizontal axis, and excuse the units of being kilograms per meter cube, 6 kilograms per meter cube is 10 pounds per cubic yard. But we'll see with mortar bars that we need actually a very specific. We have small mortar bars stored over water. We need quite a high alkali content to initiate expansion. Larger prisms stored in a similar way over water, we still need quite a significant amount of alkali to initiate expansion, but our large blocks exposed on the exposure site will expand at a much lower alkali content. And as Kevin Folliard mentioned last week, this is a problem with alkali leaching. The smaller the sample, the more leaching you get, and therefore the more alkali you need to put into your concrete to compensate for the alkali that's leaching out. In field exposed structures with large concrete elements, the leaching is insignificant. Another example that you saw last week, and I'm being deliberately repetitive here because I know this was a week ago. This is data from the University of Texas exposure site, where they found expansion with this specific aggregate, a very highly reactive aggregate called Joe. They found expansion both with high alkali cement, as you can see here, and also with low alkali cement. However, in the laboratory, only the prisms with the high alkali cement expanded. The prisms with the low alkali cement did not. So we know we have this disconnect between the laboratory and the field with regards to the alkali content required to initiate expansion. Given that we don't have a decent method, a reliable method for establishing the threshold alkali level for a given aggregate, what the tendency has been over the recent years is for specifications to actually use empirical values. AASHTO PP65, for example, uses an alkali limit that ranges from 3 to 5 pounds per cubic yard, and the actual limit depends on the risk of alkali silica reaction and the classification of the structure. We'll talk more about that later. And these limits have basically come from experience, mainly from field experience, by looking at structures that have alkali silica reaction and determining what the minimum level of alkali is, or the alkali level is in that structure. It's been possible to come up with some kind of indication of how much alkali we need to initiate alkali silica reaction in the field. So if we have so far two options, looking using non-reactive aggregates, controlling the alkali content of the concrete. We're now going to look at a third option, which is the use of supplementary cementing materials. By supplementary cementing materials, here we're talking about fly ash, slag, silica fume, or natural pozzolans. We have known about the ability or the potential for natural pozzolans to control alkali silica reaction, again, ever since Stanton's very first paper in 1940. Stanton showed us that the pozzolanic cements could be an effective control. This actually shows some of Stanton's data. What he's plotted here is expansion of his mortar bars stored over water as a function of the replacement level with different pozzolans. So you can see here, this would be his control sample. That's expansion of the mortar bars without any SEM. And you can see by partially replacing the cement with relatively small amounts of a calcined shell, he could control expansion by the use of 10 to 20% calcined shell. The pumicite he used, the ground pumicite, required slightly more, maybe sort of 30 to 40%. Stanton was a pretty smart guy, and he thought, well, am I merely diluting the cement? Is that why these materials are working? Because I have less cement in there. So he tested an Ottawa sand, basically an inert Ottawa sand, pure silica sand. He ground that to cement fineness and substituted the cement for that, and actually found that at very low replacement levels, up to 20%, he saw almost no reduction in expansion, but then eventually he did see an impact of dilution. But as you can see, the pozzolans are having a far bigger effect than just straightforward dilution of the cement, meaning that the pozzolans are having a benefit of controlling ASR beyond mere dilution. If we look nowadays at the vast amount of literature that's been published on the use of SEMs to control ASR, the general conclusion that almost all of these materials can be used to control ASR, providing that they're actually used in sufficient quantity. So I guess the question is, how much is sufficient? And the answer to that is, well, it really depends. It depends on a number of different parameters. You'll have to excuse me while my computer catches up. This graph here shows, I really do need to go back a bit here. This is, excuse me a minute here. I do apologize. I don't know why. I can only think it's something to do with WebEx. I never have these kind of problems with my computer normally. Okay. For some reason I now can't control that. Okay. So here we have a sort of conceptual look at we have expansion plotted here against replacement level here. Some SEMs, silica fume or metakaolin might be good examples, are very efficient, and they'll control expansion at relatively low levels of replacement, maybe 10, 15, or certainly less than 20%. At the other end of the scale, we have SEMs that may not be very effective at all at low levels of replacement, and we may need to get to levels of replacement like 40 or 50%. And paradoxically, it's the silica content of the SEM that determines how effective it is in terms of controlling alkali-silica reaction. The more reactive silica an SEM contains, the more effective it is. And that's because really the reaction, the initial reaction that occurs between a pozzolan and cement is really a form of alkali-silica reaction. The silica in the pozzolan is reacting with the alkali in the cement and eventually producing CSH. But in that process, it consumes some of the alkali. So the SEMs that are very high in silica, reactive silica, like silica fume, will be effective here. SEMs that are much lower in reactive silica, like a class C fly ash or a slag, will be over here. A class F fly ash, for instance, might fall somewhere between the two. So the silica content of the SEM is very important. When we look in more detail, we actually find out that the ability of an SEM to combine alkalis is a function of its calcium-silica ratio. So the calcium content is also important. But unlike silica, the more calcium we have, the less effective the SEM. Of course, another thing that controls the effectiveness of the SEM is the alkali content itself. If we have SEMs that are very high in alkali, clearly they're going to be less effective because they're bringing about a better challenge, bigger challenge in terms of controlling the alkali content. The other parameters that seem to control the amount of SEM required are the nature of the reactive aggregate, and generally more reactive aggregates require more SEM, and also the amount of alkali in the system from the Portland cement. If the cement's contributing a very large amount of alkali, again, we might need more SEM than we do if there's a lower amount of alkali. So in summary, we basically need more SEM. The lower its silica content and the higher its alkali and calcium content, and also the higher the reactivity of the aggregate. Let's look at some real data now, and this is data from a concrete prism test, so we can see the data goes out to 2 years. We have expansion up here. This is the control sample with no SEM at all. We have the silicious limestone aggregate here. For those of you who are familiar with ASR testing, this is the commonly used sprat aggregate. And we can see we get very rapid expansion with this aggregate, and we're seeing damage in a matter of 1 to 2 months. We're passing the limit after 1 to 2 months. If we now substitute 25% of the cement with a low calcium fly ash, we can see that we're very effective in controlling expansion, and we actually pass the 2-year limit is commonly used at 0.04%. We're doing this despite the fact that this fly ash has an alkali content which is higher than the alkali content of the cement that it's replacing. So again, this is indicating the fly ash is doing something beyond just mere dilution. We've known about the ability to fly ash or class F fly ash, low calcium fly ash, to control ASR for a long time. In addition to many lab studies, there's been many field studies like this one here. This one shows cubic yard size specimens, so these are 1 by 1 by 1 yard. They're 18 years old. The photograph on the right shows a concrete without fly ash, and the photograph on the left shows a concrete with 25% fly ash that was added on top of the cement. So it wasn't replacing the cement. So the actual cement alkalis in this block are the same as in the block to the right, and yet the fly ash is still able to control expansion and cracking. Going beyond exposure site studies to real field studies, we actually have further evidence again of the ability of fly ash to control ASR. This is a nice example here in Ontario in Canada. This is the Lower Notch Dam, which was completed around about 1970, and is probably one of the first, if not the first, ever known case where fly ash has been used deliberately with a highly reactive aggregate and a high alkali cement to control ASR. This is another example here of having to use the reactive aggregate. They knew this aggregate was reactive, but when they constructed this dam here, they had to excavate a huge amount of rock from here to make to construct the intake channel, and economy dictated that they should use this aggregate if they could. The nearest source of non-reactive aggregate was something like 200 kilometers away, so it really wasn't feasible to use something else. They did know this aggregate was reactive. Other structures in the neighborhood were also showing, a lot of the existing structures in the neighborhood were showing severe signs of alkali silica reaction when this structure was built. So they were well aware of the problems with alkali silica reaction at the time of construction. For some reason, I seem to be jumping over slides there. I'm not quite sure why that is, but if you bear with me, I'm just going to make a few corrections here. Excuse me for this, I do apologize. Just to show you, here are some structures in the same location that were built with the same type of aggregate from the same outcrop. This is basically a gray wacky argillite aggregate, and almost every structure, every major structure, highway or hydraulic structure in the neighborhood was showing significant signs of alkali silica reaction. Yet they went ahead and constructed the structure. They had a little bit of luxury of time, and they had about 3 years to be able to experiment with different options prior to construction. They built some blocks and put them in their lab. And you can see here, this is the expansion of the concrete with a straight Portland cement mix. And you can see the green line here shows the expansion, the same aggregate but using a low alkali cement. And then the blue line shows the expansion using a high alkali cement and the same cement as the one here, but using fly ash too. And they saw where they had the comfort of just 3 years of data, and they decided to go ahead with this option here, high alkali cement plus fly ash, and they built the structure. We went to revisit this structure last year. It's 40 years old, and after 40 years, it's standing up very well. Not a sign of ASR, no cracking on the structure, well, apart from minor cracking that's not really attributed to alkali silica reaction. And it would seem that fly ash has proven itself over the past 40 years as an effective preventive in this case here. Another example of in real structures is provided by this case here in the United Kingdom. This is a hydroelectric scheme, and there are 2 dams in this hydroelectric scheme that were built with the same aggregate. This dam here, known as the Dinas Dam, the one in the middle, after something like the order of 20 years, was showing very extensive damage due to alkali silica reaction. I really do apologize for this. The Dinas Dam shows very extensive damage due to alkali silica reaction in the form of very, very severe cracking. The dam's growing at somewhere in the order of 5 millimeters a year upstream because it's an arch dam. Upstream, they constructed using the same aggregate, cement with similar alkali content. This time we used fly ash in the concrete, mainly to control heat. They didn't really know anything about ASR at the time they were constructing this dam. They used fly ash to control heat, and 50 years on, this dam is now 50 years old, the fly ash concrete is still in excellent condition despite the use of the same cement and the same reactive aggregate. So another nice case history that's showing the ability of fly ash to control alkali silica reaction. Okay, so we're going back to this graph here. We've seen, this is our result we saw earlier for the low calcium fly ash. What this graph shows us is that not all fly ash is created equal, and we can see the fly ashes that are higher in alkali content, let me repeat that. Fly ashes that are higher in calcium content are less effective in controlling alkali silica reaction. All of these are at 25% level of replacement, as you can see here, but as the calcium oxide content of the fly ash increases, it seems that the ability of the fly ash to control ASR diminishes. This graph actually shows things plotted in a slightly different way. We now have expansion at 2 years, plotted as a function of the calcium content of the fly ash. And what we can see is the fly ashes that were considered to be class F, they are fly ashes with typically less than 20% calcium oxide, are all relatively effective at this 25% replacement level, but as the calcium content increases above 20%, we can see the ability of a fly ash to control alkali silica reaction diminishes. This doesn't mean that these fly ashes cannot be used to control ASR. What it means is that these fly ashes have to be used at a significantly higher level. The blue lines here show a series of different fly ashes able to control alkali silica reaction when they're used at a 20 to 30% replacement level. Despite what this says here, this is actually the fly ash replacement level down here. And you can see for our class C fly ashes in red, we need somewhere upwards of 50% or so to control expansion. So class C fly ashes are less efficient in this role. They have to be used at a higher quantity. What about slag? Well, this is another graph showing us expansion as a function of age. And here's our control again, similar to the last control. And we can see we can control ASR by using increasing amounts of slag, 25, 35, but we might need to get somewhere above 35% to actually control expansion. In this case here, 50 and 65% are working very well. I'm going to use slag as an example of the impact of aggregate reactivity. And what we can see here is basically expansion at 2 years for 4 different aggregates as a function of the slag level down here. So these 4 data points here are all the control samples with no slag, and you can see that the 4 different aggregates listed over here expand by different amounts as might be expected. With 25% slag, again, we're getting different amounts of expansion. We can see that 50% slag is effective with all 4 aggregates, but some of the aggregates respond okay at 35%. So the amount of slag you need is a function of aggregate reactivity. We would also find this with fly ash and silica fume and natural pozzolan, but in the interest of time, I'm giving examples of the aggregate reactivity with the slag. I gave examples of the impact of the SCM chemistry with fly ash. Okay, what about silica fume? Well, silica fume, again, it depends on how much you use, and you need to use a certain amount to control ASR, of course. Again, we have expansion versus age. Here's our control sample. What we're finding here is that the sort of level of silica fume that's typically used in construction when silica fume is used on its own, 7.5% or so, is not quite enough. In fact, 10% might even be borderline. And to be perfectly safe, we need to get somewhere in excess of 10%, which of course makes it difficult to use silica fume. Using levels in excess of 10% is not normal standard practice, as it creates some other difficulties with handling and placing and finishing the concrete. So silica fume would tend to be used in addition to other SCMs, as I'll show you later, in a ternary system. Of course, we have to remember that this high level of silica fume that we need here is required because we're using a highly reactive aggregate and a very high alkali cement. And it may well be with less reactive aggregates and less alkali from the cement, we can control expansion with slightly lower levels of silica fume. We're going to use silica fume as an example of the effect of the alkali content in the concrete. And what we have here are two graphs with different levels of alkali. Here we have an active alkali content of less than 7 pounds, and here we have one of over 8 pounds. So an increase in alkali content as I go from the left to the right-hand slide. These graphs show expansion as a function of age for 12-inch concrete cubes placed on an external exposure site in South Africa. What they show is with the lower amount of alkalis, 7% silica fume has been effective after 7 years in controlling expansion. But when we go to the higher amount of alkalis, we're going to need more silica fume. 7% isn't enough. So I think between this series of slides, we've seen examples of how we need different amounts of SEM depending on the composition of the SEM itself, the amount of alkali available from the cement, and of course the reactivity of the aggregate. This slide here just shows the impact of a ternary blend using silica fume in combination with something else, and what we're doing here is showing an example for silica fume and slag. What we tend to find is that when you combine two supplementary cementing materials together, you can reduce the amount of each SEM roughly in proportion to the amount that you would typically use them in. So, for instance, if you might need somewhere in the region of 8% silica fume or 44% slag or something like that, if you put them together, you can get away with half the amount of each. So the effects of each SEM are kind of additive. If you were to put 3 SEMs together, you could, and you determine the minimum quantity required of each of them, you could put 3 of them together and use a third of each of those minimum quantities, and again, control ASR. So the effects are kind of additive. Well, how do SEMs work? Well, to really understand that, we have to go to look at the actual composition of the pore solution in the concrete. That's the fluid phase in our concrete. That's where the alkalis, the active alkalis, the alkalis that are going to attack our aggregates actually reside in the pore solution. We can actually physically extract the pore solution from concrete or mortars or paste by putting it under very, very high pressure in a press. Typically, we use pressures in the order of or in excess of 65,000 psi or 450 MPa. At that very, very high pressure, we actually squeeze the juice out of the concrete. And we can then analyze that juice. And that's shown on this graph here when it finally appears. Excuse me again. I do apologize for this. I really don't know why it's happening. Okay, so this shows the alkali content. Basically, this graph here shows the alkali content of the pore solution expressed as the hydroxyl concentration. If you remember from last week when we talked about the fundamentals of alkali-silica reaction, the risk of ASR was a function of how much hydroxyl ion, OH, we had in the pore solution. So this shows the hydroxyl ion concentration as a function of the age of the sample. And we see our control sample up here in black, and what we see is a very, very high hydroxyl ion concentration. This is a paste sample, so there's no reactive aggregate, and that high concentration is maintained throughout the period of testing. If we look at a low calcium fly ash down here, the green line, we can see that the amount of alkalis in solution are much lower, much lower than in the control sample, despite the fact that the fly ash contains alkali, significantly more than the cement. And this again is because the fly ash is reacting with those alkalis, consuming them, taking them out of solution so they're no longer available to react with the aggregate. And what we can see is as we increase the calcium content of the fly ash, like this example here, the fly ash becomes less effective in this role. As we saw, it was less effective in terms of controlling expansion. This graph shows a similar situation for silica fume. Silica fume is also very effective in this role. It's effective much faster because silica fume has such a high surface area and there's such a large amount of reactive silica. We get a very rapid reduction in alkalinity. At low levels of silica fume, there is a bit of concern that some of this alkali is regenerated as the silica fume, as the alkali silica fume complex is converted to calcium silicate hydrate. This doesn't happen in the presence of fly ash. So we put a little bit of silica fume and fly ash together. The silica fume will produce a very early reduction in pore solution alkalinity, and the fly ash keeps it low, making these ternary blends with either silica fume and fly ash or silica fume and slag very effective in terms of controlling the pore solution and, of course, expansion due to alkali silica reaction. So, again, what does all this mean? Well, what it means is that another way to explain this is to look at the impact of using reactive silica in mortars. What I want you to do is to concentrate on the bottom half of the slide first. What we're seeing here is a mortar bar. The blue line shows a mortar bar with Portland cement and Pyrex glass, which, as we discussed last week, Pyrex glass is a highly reactive form of silica. It's been crushed to sand size, so this is essentially the ASTM 441 Pyrex mortar bar test. And you can see we get very, very rapid expansion with this Pyrex glass. After 8 weeks, we're up to 0.4%. The red line shows essentially the same mix. It has the same Pyrex glass as a sand. But we've taken a little bit more of that Pyrex glass and we've now crushed it to cement fineness. We've crushed it to pass a 75 micron sieve, so it's the same fineness as cement. And we've substituted some of the Portland cement for the Pyrex glass. Basically, we're using the Pyrex glass as a pozzolan because that's essentially what a pozzolan is a finely ground reactive silica. And now we can see that the Pyrex glass, the ground Pyrex glass, is actually decreasing expansion with the same sand-sized Pyrex glass. So what we're seeing here is if we take reactive silica and it's in a sand size fraction, we'll get expansion. But if we take it and grind it very finely, it will act as a pozzolan and help prevent expansion. And in fact, the reverse is true. What the top half of the slide shows here is if we take a reactive pozzolan, a very finely divided, efficient pozzolan, and we allow it to agglomerate into sand-sized particles, which is what we're seeing here. We have a sand-sized particle of silica fume. Many millions of individual silica fume particles have kind of glued themselves together to form a sand-sized particle, close to sort of 0.5 millimeter in size. This is now acting as a reactive aggregate. And actually, silica fume is causing ASR instead of actually preventing it. So really, it's a question of size. Very finely divided reactive silica will react with the alkalis in much the same way that we have ASR, but that any reaction product is so finely dispersed throughout the concrete that we don't have any individual accumulations of gel that can create stress to form damage or cracking. Not only that, the reactions occurring at such a fine particle size level, the gel that forms quickly converts to calcium silicate hydrate, the second half of the pozzolanic reaction, if you like. And this consumption of the alkalis, the very finely divided silica, occurs before the alkalis can actually attack the larger particles of reactive aggregate. So it's a competition, if you like, between the pozzolan and the reactive aggregate. Fortunately, provided we have enough pozzolan in there, the pozzolan will win. So what about testing of pozzolans? We've seen that we need various amounts depending on a number of different parameters. How do we test them? Well, of course, we have different ways of testing them. We can use the accelerated mortar bar test or the concrete prism test. They're the two laboratory test methods that tend to be used the most. Of course, the accelerated mortar bar test is used a lot more than the concrete prism test. And I think we learned last week a lot about these different test methods and their reliability to control their reliability for evaluating SEM, so I'm only going to repeat very briefly some small aspects of that today. One of the things that we learned last week was that there isn't a great correlation between the expansion of the concrete test and expansion in the mortar bar test. We did have aggregates that gave different results depending on how we tested these, and I think Kevin referred to these as our bad actors. Well, just to remind you, if we do have good actors, these are the aggregates that give us the same result in both tests. In other words, they fail both tests, or they pass both tests, of course. If we test aggregates that give us good behavior and perform well in both tests, it is acceptable to use the accelerated mortar bar test to evaluate the amount of SEM that we need to control alkali silica reaction. And this is shown on the next graph. If we can get to the next graph. And what this graph shows us here, it's a little bit confusing, so I'll explain it. It shows, if we concentrate on the red lines, what we're seeing here is the expansion of concrete at 2 years, plotted as a function of the calcium content. Here we're using actually a high calcium fly ash, it has about 30% calcium. So concentrate on the red lines. This is our control mix without any fly ash. Here we go to 30%, 45%, and 60%. And if we interpolate that data, we need about 50% of this fly ash to control expansion in the concrete. Looking at the blue lines now, we have our axis over here, expansion of mortar bars. Here we have no fly ash, again 30%, 45%, and 60%. And we need about the same amount, maybe slightly more in this case here, to control expansion of the mortar bar test. So we do get similar results in the concrete test and the mortar bar test for those good actors. I think they were the Jack Nicholsons in Kevin's slides, if you remember that. And for this reason, when we go next to the AASHTO test, you'll see that in the AASHTO approach, we do recommend the use of the accelerated mortar bar test for evaluating the amount of SEM you need, providing it correlates well with the concrete prism test. And what we're suggesting or recommending in AASHTO is that you test your aggregate in both tests. If it falls in the good actor zone here, then you can use the accelerated test to try to find out how much slag, fly ash, silica fume, combinations thereof that you would need. And so that's the recommendation. Okay, we're coming to the end of our discussion of preventive measures, and the last thing we'll discuss is the use of lithium compounds. We've known for more than 50 years now that certain lithium compounds, in fact most lithium compounds, can be used to control alkali silica reaction. This was a discovery made by McCoy and Caldwell from the Lehigh Cement Company, who, back 50 years or so ago, actually used the Pyrex glass expansion test, so made mortar bars of Pyrex glass, and literally hundreds of different chemicals from their chemical storage cupboard in their laboratory to try and determine what would work to actually control ASR. Now, of all their testing, they found that lithium was the most effective chemical to do this. We now know that most of the different compounds, lithium compounds, can be used. The preference has emerged over the last decade or so to use lithium nitrate, mainly because it doesn't increase the pH of the pore solution. So it tends to be the more effective of all the lithium-bearing compounds. This shows McCoy and Caldwell's data, well, some of their data for lithium. What this shows here is the expansion of mortar bars here, plotted as a function of the control. And the control would be the mortar bar without lithium, so that's this mortar bar here. So obviously, its relative expansion compared to itself is 1. And you can see the impact of increasing the amount of lithium. But what McCoy and Caldwell found was it wasn't just the lithium content that determined the amount of expansion. It was the lithium content divided by the sodium and potassium content. So basically, the more sodium and potassium, the more alkali from the cement, the more lithium you needed to control expansion. And McCoy and Colwell suggested that that ratio of lithium to alkali, sodium and potassium, had to be somewhere in the region of 0.74. They proposed this 0.74 value, which has kind of become what we sometimes refer to as the standard dose of lithium to control ASR. Since then, there has been a lot of work on concretes with real reactive aggregates rather than just with mortar bar. I'm just going to show you very briefly some of that data from this particular study. I'm showing this because I was involved in it, so it's easier for me to get hold of. This is quite an extensive study that was conducted in the UK, looking at blocks on the exposure site, as you can see here, and also prisms and laboratory conditions. And this data basically showed that McCoy and Caldwell's data could be repeated for real aggregates, for actual real concrete aggregates, which is encouraging. So you can see here we've got a series of different reactive aggregates, different lithium contents, and again, we're seeing that the lithium-bearing compounds are effective, and this lithium to alkali ratio seems to be the controlling factor. So lithium is effective. Is it effective with all aggregate types? And that's a question that we asked ourselves in Canada before we were at the stage where we wanted to include lithium into our specification. So we looked at a range of different aggregate types. I'm going to show you results for 12 different reactive aggregates, 13 in total if you include this one here, which is a non-reactive aggregate. I'm going to start off with 6 aggregates. This shows the expansion of these 6 aggregates here, plotted against the lithium dose. And this 100% value here of the standard dose, that represents a situation where the molar ratio is 0.74 lithium to sodium plus potassium. So with 6 aggregates, we actually found that we really were able to control expansion very, very effectively. 3 of our 12 aggregates, though, actually required significantly more lithium, in some cases up to 50% more lithium. And then the 4th, another set of our aggregates, another 3 of our aggregates, didn't work effectively, even at 25% more or even 50% more. So what we learned from this is that the lithium dose required is actually highly dependent on the aggregate that you're actually using, and that 100% dose does not work with all aggregates. As a consequence of this, in the Canadian standard, we basically moved away from allowing lithium to be used on a prescriptive basis, and we require a performance test. We actually require that the aggregate be tested with the lithium to determine how much you actually need. And that says in writing what I've just already explained, so I'm going to cut over that. Okay, so let's summarize our presentation on alkali silica reaction and preventive measures. The use of non-reactive aggregate is the most obvious choice, but may not be viable in some cases. Limiting the alkali content of the concrete is effective, providing that the safe level of alkali can be determined for a specific aggregate. And if we can't determine that, we basically have to use empirically derived minimum, or I should say maximum alkali levels. Supplementary cementing materials are effective, providing they're used in sufficient quantity. And the amount required depends on the composition of the SEM, the reactivity of the aggregates, and the alkali loading in the system. Lithium is effective with some but not all aggregates, and the amount of lithium required has to be established for each aggregate type. So again, that's the end of the presentation. I really do apologize for the lag in the slides. I'm pretty sure it's not my computer. But anyway, I'll pass it over back to the moderator of the session. Thank you.
Thank you, Dr. Thomas. Yeah, I think we might just be experiencing a little bit of lag, probably due to connection speeds, but I think it's going okay. We do have quite a few excellent questions that we'd like to get to regarding this presentation, so I'll get right into those. We also have Dr. Fournier on the line as well, and he and Dr. Thomas will take these questions as I repeat them. The first question we have is, at what point in time will the expansion stop? Is there a time when all available alkali and silica is consumed and expansion will stop?
Yeah, that's a good question, and of course the answer, like the answer to everything else, is it depends. It really depends on the nature of the aggregate. If there's only a small quantity of silica in there, then it is possible that you can run out of steam, if you like, run out of reactive silica. And I've seen cases where after 10 years or so there hasn't been any sign of further expansion after monitoring them for 10 years. However, with some aggregate types, there's a potential for the, if you have enough reactive silica in them, there's a potential for the reaction to proceed for almost indefinitely. We've monitored dams that are 70 or 80 years old that are still expanding. The alkalis, I mean, people often think the alkalis might be consumed. The alkalis to some extent are recycled. It's almost like the pozzolanic reaction again. The initial alkali-silica reaction produces an alkali-silica gel, which will slowly, the alkalis will exchange for calcium. Some of those alkalis get recycled and go back out and cause further damage. And in a large structure where there's no opportunity for the alkalis to leach out of the structure with time, as I say, we've seen expansion continuing even after 70 years of age. In addition to that, there are some aggregates that will release alkalis very slowly themselves. And even though that happens over decades, it doesn't happen in the short term, again, it can contribute to continuing long-term expansion. So the answer to that is it really depends on the specific situation. Where you only have a small amount of reactive silica, or perhaps where you have a very slender element where leaching can take place, then the reaction might exhaust itself in a decade or so. But in other cases, it's continued for almost a century. So I know that's not a perfect answer, but I'd like to ask Benoit to contribute to that too.
Dr. Fournier, do you have anything to add to that? Okay, if not, we'll move on to the next question. Have you been able to correlate critical alkali content with the results of other tests such as C295, C1293, or even C1260?
Not really. We've done a lot of work trying to run, for example, 1260 with different molarities in the soap solution. And different aggregates definitely respond differently. Some aggregates will react when at a pH of 13.2, some at a pH of 13.4. So they will respond differently. But we don't really have the benchmarking data to know what alkali contents they expand at in the field. So it's been hard to really correlate that. With petrography, then, yeah, I guess that's been a little bit more successful to the extent that we know that our highly reactive forms of opaline silica will react at relatively low alkali contents. And I'm talking about maybe around about 3 pounds per cubic yard. But some of our aggregates that react because of microcrystalline quartz or strain quartz, such as grey wackies, may require in excess of that amount. They may require 4 or 5 pounds per cubic yard. But a lot of this is kind of like, it's sort of empirically based. I'd be very hard pressed to put a sort of scientific relationship to that. But it certainly seems like the more reactive forms of silica, like the opaline silica, maybe the volcanic glasses, are certainly would react at a lower alkali content than microcrystalline or strained quartz. But beyond that, it's difficult to establish a very firm relationship.
Okay. The next question is, what is the aggregate type and what mineral is the culprit causing expansion at the McTackwick Dam?
The aggregate's a gray wacky type aggregate, gray wacky / argillite. So the reactive component is basically strained quartz, and maybe some microcrystalline quartz too. But essentially, it's predominantly strained quartz. Benoit is our photographer on our team, so I would definitely like to refer to him. I have a feeling we might have lost him now.
Dr. Fournier, are you there? Okay, we may have lost him. Go ahead and move on to the next question then. It's, what was the alkali in the cement for the control on your slide 24?
Let's see. Just give me a second to go to that slide. Yeah, this test has basically been run in accordance with the 1293 test. So the control is produced with a high alkali cement. By specification, it's between 0.8 and 1%, and then it's raised to 1.25% by addition of alkali to the mixed water. So that would yield an alkali content of 5.25 kilograms per meter cube, and somewhere in the region of 8 pounds per cubic yard. £8.7 per cubic yard.
Okay. The next question, is the fly ash from 50 years ago the same as today's fly ash, or have mining, processing, or pollution controls resulted in material changes?
I think it's essentially, certainly the fly ashes from bituminous coals are the same as they were from decades ago. We're now exploiting different types of coal. There's more softer coals being used in power stations now. So that means there's more subbituminous and lignite coals, which means that there tends to be a greater abundance of high calcium fly ashes now than there used to be. So certainly that's changed. But fly ash produced from a given coal source wouldn't be that much difference because of processing controls. Some stations are running low NOx burners nowadays. That might tend to have a slight impact on reactivity and possibly carbon content. But the main change is the different source of coals that's used. Of course, some other stations are injecting things into the boiler for emissions control, and that can impact the fly ash too. But generally, the fly ash is free from any of those processes. It's still produced from bituminous coal. It's going to be the same as the fly ashes that were used, 50 years ago.
Okay. Next question is, how would fly ashes with low calcium oxide and high alkali content control ASR?
Well, you tend not to get fly ashes with low calcium content and high alkali content. The ones with very high alkali content tend to have moderate calcium contents. But it is, if you did have a low calcium fly ash with a high alkali content, then what you will find is as the alkali content increases, you're going to need more fly ash. And eventually you'll get to the point where you can't put enough fly ash in because its alkali content is too high. So basically, it's if you like it, the more alkali you have in the fly ash, the more silica you're going to need to combine with that fly ash. But if the alkali content gets too high, you're just not going to be able to achieve it. So eventually, you'll get to an alkali level where you can't control no matter how much fly ash you put in.
Okay, we'll move right along here. Next question is, explain the meaning of the graph when an aggregate tested with C1260 has expansion above 0.1% at 14 days and the C1293 expansion is less than 0.04% at 1 year.
Yeah, I think that's actually quite disconcerting. I mean, you know, these are the aggregates that Kevin referred to as very bad actors. Fortunately, there's only a few of these aggregates. So these are aggregates that essentially will pass the 14-day motor bar test and fail the concrete prism test. Many of these are coarse aggregates. In some cases, it's a case of when you actually crush the coarse aggregate to produce a fine aggregate for the accelerated test, you're changing the texture of the aggregate, and you know, that could have an impact. Or you may even crush the aggregate and actually lose the reactive phases. There's a number of famous aggregates that will do like that, like the Potsdam sandstone. By crushing the aggregate, you lose the reactive silica that's holding the individual sandstone grains together. So that's another reason. And perhaps the reason we're finding more recently is it may well be a pessimum effect. You know, the pessimum effect, there are some aggregates that will produce more expansion when they're used not as the total aggregate. They'll produce that maximum amount of expansion when they're only present at 30, 40, 50, 60%. And then they're used at higher levels, the actual amount of expansion decreases. With an aggregate that displays the pessimum effect, if you use it in the concrete prism test as a coarse aggregate, it's going to be there in a lower proportion than it is when you use it in the accelerated motor bar test when you're using 100% of that aggregate. So the pessimum effect could also have an impact on this as well. So there are basically three different. It's the processing, the potential for losing the reactive silica, and this pessimum effect. I don't know if that's a very adequate explanation.
Okay, actually we do have a little bit of clarification from that attendee that asked that question. So let me just state this. He says, I'm asking about the use of supplementary cementitious materials as determined in C1567 to mitigate a failing 1260 but passing 1293. He says that would be the area showing the number 13 there on the slide.
Okay, I'm not sure. Let me try to answer that question. If you were to test these aggregates, these ones that fail in the concrete prism test but pass the motor bar test, these aggregates can still be controlled. 1567, if you tested them in 1567, they would still pass the accelerated motor bar test. I'm not quite sure I understand the question. You could still reduce the expansion in the concrete prism test with these aggregates. But if you run these aggregates are already passing 1260, so they would obviously pass 1567 as well. So I'm not quite sure I understand that question. I don't know if there's any other clarification, or we can maybe deal with this offline.
Okay, well, yeah, let's move on to another question, and we can follow up on that after the sessions. Next question is about the cost of using slag aggregates. I think the availability of slags are fairly limited in the western USA. Would you recommend any specific methodologies or software to evaluate the cost differences between the various secondary supplemental cementitious materials?
Well, first of all, we're not talking about slag aggregates here. We're talking about slag as a cementing material. I'm sorry that wasn't clear, but all the slides here with slag were referring to supplementary cementing materials. So that's ground granulated blast furnace slag. It's not slag aggregate. Slag aggregate would be a whole different issue. From the point of view of costs, I'm afraid that's really not really part of this workshop. That's really going to vary from one location to another across North America. But the choice of materials, the impact on prices, that's something I think every individual producer has to deal with himself on a daily basis. So I really couldn't determine what the cost implications were without actually knowing what all the costs of all the raw materials are in the different locations. And even then, I would have to add that the cost is not really my forte. We're really dealing with the technical issues here. So I'm sorry for that.
Okay, understandable. We actually had a couple attendees who asked a similar question, and that is, have you ever tried or considered the use of expanded shale, clay, or slate lightweight fine aggregate as a preventative means to ASR expansion?
I haven't myself, but I know this is this. In fact, my colleague at the University of New Brunswick, who's now retired, has done work in this area, and I believe there can be a positive benefit. I'm not sure whether it would completely suppress expansion or not, or whether it would just be a partial benefit. I am involved in a research program that's just been started at the Oregon State University that's aimed at addressing exactly that question. So I think for the time being, I'd like to defer answering that question. But there certainly is a partial benefit. I think that's been established. But under what conditions you could get complete prevention, I think we have to determine that.
Okay, next question is, what amount of expansion level due to ASR will be deleterious and reduce the durability of the concrete?
What we tend to use for test methods, we've always used a 0.04% at 1 year for testing aggregates, at 2 years for testing concrete. There's nothing magic about that number. It just happens to be the onset of cracking in a concrete prism test generally. As I say, there's nothing really magic with that. And obviously, in most structures, anything that produces cracking is going to be deleterious, because that's the point at which you're going to allow other mechanisms to kick in, whether it's freeze-thaw opening up those cracks or chlorides penetrating down the cracks to the rebar. So anything that produces cracking is going to be deleterious. Putting a magnitude on that, beyond that 0.04% that I mentioned, 0.04%, for instance, would be disastrous in a dam. That's a lot of expansion to deal with in a massive structure. But then you have to remember that these are expansions under completely restrained conditions, and if you had any type of constraint at all provided by reinforcement, or it was a much slower expansion, so creep would relieve things. And I think these concrete mixtures that are producing 0.03% in the lab probably wouldn't do so in the field, and almost certainly wouldn't do it if there was any kind of resistance or restraint to that expansion. So the simplest answer would be anything that produces cracking. And I think that's probably the simplest summary I can give to that.
Okay. Next question is, 60 years later, in the case of the dam that is being replaced in 2030, what effect on the strength of the concrete has occurred with the ASR damage to date?
Well, that really depends where you are in the structure and how much expansion and cracking has taken place there. Generally, I would say that with that particular case, although the impact of ASR has been huge in terms of managing the structure, in terms of jamming turbines, closing gates, it's been a disaster in terms of trying to operate the structure. If you take cores out of a structure, the changes in mechanical properties have not really, certainly in terms of compressive strength, are not really that significant. I did some testing on cores from that structure quite a while back, and we saw very little consistent change in compressive strength. A slight reduction in stiffness. I mean, you would expect that. Maybe depending on where you are in the structure, 20 or 30% reduction in stiffness. But again, you have to temper that with the fact that whenever you take a core out of a structure, you've taken it out of its stress field, and any reduction in mechanical properties are going to be much greater than would actually be in situ. I would say to a great extent that changes in mechanical properties are not really the significant issue with that structure. It's dealing with the growth and the expansion and the cracking. That's really the problem. I don't think there's really been any indication that the structural performance of that concrete has been drastically affected.
Okay, the next question is, have you considered raising the alkali content in the laboratory testing to compensate for the leaching?
Yeah, well, that's perhaps the next option. And essentially, that's what we've been doing over the past 20 or 30 years as a test method has evolved. You know, that test started off as I think a mix with about 5 or 6 sacks of cement and just, you know, whatever high alkali cements available in the neighborhood. The cement content and the alkali content of that cement have crept up with time. You know, as I say, the test has evolved, and maybe that's the next step is to go even higher. I'm not sure if that would resolve the problem, and essentially it will help to compensate to some extent. But of course, the higher the alkali content in the concrete, the larger the gradient, the faster it's going to leach, just because you've got a higher alkali content. You know, it's obviously something to consider, but I really think that the secret for us is to try and develop an exposure condition where the leaching is minimized or eliminated. I think that would be the preferred approach. Another issue with the leaching is the rate of leaching depends on the SEM that you have in the concrete too. So you'll get more leaching with a straight Portland cement mix than you would do with 20% fly ash, and you'd get even less leaching again with 40% fly ash. So trying to compensate for the leaching is actually very difficult. Trying to minimize it or eliminate it is probably our preferred way of moving.
Okay, the next question is, are adding supplementary cementitious materials like Class F fly ash just changing the chemistry of the silica gel to make it non-expansive, or at least delaying the expansion?
No, I don't believe that's the case. The gel that does form, when it does form with that SEMs, will still be the same. I really think that the main reason SEMs work is by lowering the availability of alkali in the system and preventing the formation of the gel. You definitely change the nature and the chemistry of the calcium silicate hydrates that form, and so they're the binding minerals, if you like, the cement phases. You change the chemistry of those phases, and that can impact the binding capacity of those phases. But I think essentially you're not so much changing the chemistry of the gel, you're changing the chemistry of the pore solution, which prevents the formation of the gel.
Okay, the next question is, how can you test a bagged cement concrete product for ASR when the product is already blended sand and cement?
Yeah. Good luck with that one. You certainly couldn't really do it by the concrete prism test. Well, you know, this is a case, this is something that Kevin spoke to last week with the test methods. Essentially what you would want to do with a bag mix is you're basically testing a job mixture. And we don't really have a test method for doing that. I mean, you could cast the concrete and then put it into an alkali solution like we have with the accelerated motor bar test, but you can do a concrete version of that. But if it expanded, doesn't mean that concrete would expand because you might not have enough alkali in that concrete. You could test it in accordance with the concrete prism test, but again, you haven't got enhanced alkalis in that concrete, and because of the leaching effect, you probably wouldn't see any expansion. So it's very difficult. Our test methods that we have currently today are not geared up to testing job mixes. Or I shouldn't say they're not geared up, they're just not suitable for testing job mixtures. The only thing you could do with a bad product is to make a concrete prism, test it. If it expanded, you could be sure you're going to have an ASR problem. If it didn't expand, you wouldn't know. So you could only really get a failure out of that test. If it passed the test, you wouldn't know whether it's because alkalis had leached and the test was inappropriate. So it's very difficult.
Okay. The next question is, would crushing known concrete with ASR and mixing it with some existing soil and using this as a base material be detrimental to new concrete pavement placed on top of the base?
Mixing it with soil, I'm not sure I'd want to mix it with soil to make a base, but using recycled ASR affected concrete as a base is unlikely to produce expansion of that base because you've got so much space, you've got so much void space in there. But it's really something that hasn't been looked at to any significant extent. I would expect it not to. If you ended up with very, very coarse, very large aggregate particles in your base, then yes, the future expansion of those could result in heave, I would guess. But generally, if it was a crushed base, I would expect any heave of that base due to continued expansion of the small particles of concrete, I would expect it to be very small, but I think it's something that probably needs investigation.
Okay, we'll have just a couple more before we'll need to move on to the next presentation. This question is, when signs of ASR and DEF both present, how do we distinguish which was the initiator?
The symptoms are different. Generally, if you've got cracks through you can identify reactive aggregates. If you've got cracks in your aggregates and you've got gel deposits in those cracks, the cracks extend down to the cement paste. You can be sure at least that ASR took a role, contributed. With DEF, you're generally looking for evidence of expansion of the paste, gaps around aggregate, maybe or maybe not filled with ettringite. If you find some of those features, again, you might be, it's an indication that DEF might have taken place. To try and determine which one happened first, if you can be sure they both happened, I think it's unlikely you could determine which one came first. Although in my experience, alkali silica reaction usually happens on a much faster time scale than DEF, so it's most likely the ASR came first if they're both present. I'm not sure that answers the question. Well, just to emphasize that, I think it's unlikely DEF would occur first and ASR occur second, just because of the relative timescales that reactions occur on. Also, ASR can actually initiate DEF to the extent that one of the side effects of ASR is that you're going to reduce the alkalinity of the pore solution because the alkalis are being consumed. And if the alkali of the pore solution drops, that's going to accelerate the release of sulfates from the calcium silicate hydrates where they're bound because of the heat curing. So ASR can often be a precursor to DEF. So I think it's always likely the ASR occurred first. The big question is determining if both of them or either of them actually occurred. Maybe that's something I think Benoit, certainly from a point of view of diagnosis of the symptoms of ASR, Benoit will deal with that next week. One of the techniques we found very useful to determine if DEF has been and is still an issue is if you take small cores of the concrete, soak them in water. If a small cores and any ASR, just have small cores soaked in water, further ASR is unlikely because the alkalis will leach out very quickly, but it is a way of stimulating DEF, and we've actually done that in the laboratory and written a paper on that. I'd be happy to share with the person who asked that question if we get his question in the form of an email.
Mm-hmm.
Okay, fair enough. So we will need to move on now to the next presentation. That'll be Dr. Thomas as well, and we will be covering AAR specifications. So go ahead, Dr. Thomas.
Thank you. Well, I apologize for you guys having to listen to me again. I'm sure that after an hour and a half of continuous speaking, at some point I might falter here, so please bear with me. Okay, we're going to deal with specifications now. You know, there are literally hundreds of different specifications out there. You know, basically on a state level, a provincial level, a few on a national level. If you're interested in looking at different specifications for ASR, actually, I should mention that as part of the Federal Highway program that's sponsoring these workshops, we've also developed a reference site, a website, a reference website, where you can access many of these specifications if you have an interest in doing that. But there are literally hundreds of these specifications. Basically, though, they fall into one of two categories. I was hoping that after this rest, my computer would be faster. I don't know. It's probably naive of me. Maybe it's. Okay. I think I've reached the point at which my computer is not moving on at all now. Okay. All right. Maybe we have to go that way to move it on. Okay. Well, basically, you know, despite the fact there's many hundreds of specifications, they basically fall into one of two types: either a prescriptive or a performance specification. A prescriptive specification is one that actually prescribes to you the action that you're going to take. For instance, the specification might read, if you have potentially reactive aggregates, then you have to adopt one of these measures. Limit the alkali content to 3 pounds per cubic yard, use a minimum of 12% silica fume, use a certain amount of lithium nitrate, etc. That would be an example of a prescriptive specification. Whereas a performance specification would decide the preventive measure based on some kind of test, a performance test. So, for instance, performance specification might say that you test your aggregate in the accelerated motor bar test on the concrete prism test. If it passes, you can use it. If it fails, then you have to retest it again in the motor bar or concrete prism test and find out how much of the preventive measure you need to use. So they're the sort of basic different approaches to doing this. Rather than discuss 100 different specifications, what we're going to do today is look at one specific specification, and that's the very recently developed AASHTO specification, standard practice PP65/11, and the 2011 is in fact the latest version of this specification. Before I get into this, I should note that this specification was developed from the Canadian specification. Developed from, it's not the same. I believe we've made improvements to it, moved it on a little bit, and there are some subtle differences between the two. But I would like to at least reference the Canadian standards. And for those of you who are interested in a little bit more information on this and the development of it, there is a document published by the Federal Highways Administration that describes a little bit more of the development of this protocol. So if you were to take that project report number there, I'll just highlight that, because I used to need my highlight pen soon. If you took this number here and Googled it, you would reach this document and be able to download it. It will give you a little bit more information. One of the aspects of this documentation, it deals with both ASR and ACR, so it covers them both. It actually gives both prescriptive and performance alternatives. It allows the use of reactive aggregates, providing one of the following preventive measures are used to limit the alkalis using SEMs or lithium. And the actual, if you use the prescriptive approach in this document, the amount of prevention you'll end up with depends on the risk of ASR, as defined by the reactivity of the aggregate, the nature of the structure, and the exposure conditions. I should mention, just highlight here, that the preventive measures in here only relate to alkali silica reactive aggregates. Alkali carbonate reactive aggregates cannot be used. So as the title suggests here, basically there are two steps in using this recommended practice. The first step is to determine the aggregate reactivity. So we're not even getting into preventive measures in the first part of this document. And there's three possible outcomes. You can have a non-reactive aggregate, you can have an alkali carbonate reactive aggregate, or you can have an alkali silica reactive aggregate. And then, of course, our preventive, based on those outcomes, we either accept the aggregate, we reject the aggregate, or we use preventive measures. And that's the only time we would actually go to step 2, is if we actually have an alkali silica reactive aggregate. So step 2 is for selecting preventive measures with alkali silica reactive aggregate. And now we have 4 options: limiting the alkali content of the concrete, using SEMs, using lithium, or in the very severe cases where there's a high risk, limiting the alkalis and using SEM. And as I mentioned before, the preventive measures can be determined using either performance testing or prescription. This shows the general flow chart for the first step, if you like. So the first step we consider, we'll basically go from the top down. For the first step, we can consider field history, petrographic examination, and if the results of either of these are satisfactory, we can actually go and accept our aggregate as being non-reactive with no further testing required. Beyond petrographic examination, we're also allowing for accelerated mortar bar testing, concrete prism testing, and it's really up to the user how many of these approaches they actually use. And what it states in the recommended practice is, if you want to use field history, if you have a satisfactory field history, you can go ahead and use it and accept the aggregate, but you have to accept that there is a certain level of risk with doing that. And so there's a decreasing risk of failure, if you like, the more of the testing that you actually do as you go down this flow chart. There is a little loop on this flow chart for considering alkali carbonate reaction. And the loop begins with the question, is the rock a quarried carbonate? And it's only if it's a quarried carbonate the whole question of ACR should rear its ugly head. If it is a quarried carbonate, there is a rapid test method. Involves determining the calcium, magnesium, and alumina content of the rock. And based on this composition, we can plot it on the graph and determine if we have the potential for our alkali carbonate reaction. If we don't, based on this very quick test, we're fed right back into the loop for ASR again. It's a quick screening test, and I believe Kevin covered it in test methods last week. If we decide, based on the composition, that it is potentially carbonate reactive, we come on this loop here, and then we have an option of testing it either in one concrete prism test, the 1105, which has a low alkali content, or a second concrete prism test, which is our famous 1293 test, which we have a much higher alkali content. If it passes the 1105, in other words, if it doesn't show any reaction, we can be fairly sure it's not alkali carbonate reaction, and then we can use the accelerated mortar bar test, because we've ruled out ACR. The accelerated test is not suitable for alkali carbonate reactive rocks, but if we pass this test, we know it's not carbonate reactive. If we decide not to use this test, but we use the concrete prism test, if it expands in this test, we don't know whether the expansion was caused by ACR or ASR, and we have to do a forensic evaluation of the prism after test to determine if it was ACR or ASR. And if it was ACR, we're going to basically reject the aggregate. If we decide it was ASR, we're going to allow the aggregate, provided we use preventive measures. Of course, if it passes any one of these tests, then we're going to accept the aggregate. So this is our series of tests that we would conduct depending on what. And of course, if we had a silica reactive aggregate, alkali silica reactive aggregate, we could use the mortar bar test and then the concrete prism test, just in the way that Kevin outlined last week. One of the problems, so let's talk about using fill performance. Again, I don't want to talk too long on this because it was something that Kevin covered last week, but there are certain precautions that you have to use when evaluating fill performance. For a start, you have to make sure you have a long enough fill performance to be relevant. And secondly, you have to make sure that your conditions in the field, your historical conditions, are similar to those that you're going to use in a new construction. And, you know, this is all outlined here, and it's outlined in the document. We have to be very careful with we're not using fill performance history for a more benign case than we're going to use in our new construction. So, although we allow the use of fill performance, there is a risk associated with doing this, and this is clearly spelled out in the AASHTO document. Again, we also allow the use of petrographic examination. If a petrographer looks at the aggregate and says he doesn't think there's any signs of deleterious minerals in there, then again you can accept it for use. But there's a level of risk associated with that because it is quite possible that the reactive phases were not visible to a standard petrographic examination. It is possible to have reactive aggregates that have forms of reactive silica that are so finely disseminated they can't be seen by normal optical microscopy means. So again, you have to assume a level of risk. So if you're not prepared to assume those risks, or your petrographer tells you that there may be potentially reactive aggregates, then we run our ASR tests. These are the two test methods that we discussed at length last week, our accelerated mortar bar test and our concrete prism test. If you fail the mortar bar test but you pass the concrete prism test, you're allowed to override the mortar bar test and accept the aggregate for use. If you fail them both and you're on the ASR route because we've already dealt with the carbonate issue, then we're going to be in this box here where we have to take preventive measures. So again, let's just remind ourselves, by conducting this is the first step, we're evaluating the aggregate. By evaluating the aggregate, we're going to end up with three possible outcomes. As we flow through this chart, there's three possible outcomes, reading from right to left: the non-reactive, alkali carbonate reactive, and alkali silica reactive. And based on these outcomes, again, we accept, we reject, or we prevent. So we're now going to move to step 2, the prevention box. And as we've already mentioned, this is where our two alternatives come in, our performance-based approach or our prescriptive approach. We can use the performance approach for determining the level of SEM or the level of lithium. And we can do this running either the concrete prism test or the accelerated test. We can use the prescriptive approach for determining again the level of SEM or the maximum alkali content. What we can't do is use the prescriptive approach for lithium or the performance approach for determining the alkali content for the reasons that we discussed before. So the performance-based approach, again, we would use our two test methods we've already used perhaps to test our aggregate. We would now use them to retest our aggregate, but this time with various levels of preventive measures in place to see if we can now make the tests pass rather than fail. And just a reminder, if we're going to use the accelerated test to test our preventive measure, we really want to use it on an aggregate that gives similar performance in both the prism test and the accelerated mortar bar test. I apologize for the number of times you've seen the slide, but I think it's necessary to reinforce this. Okay, so I think the performance test has been fairly well described. I think a lot of people are using it. Kevin really went over it as part of his test methods presentation last week. So let's focus now on the prescriptive approach. In the prescriptive approach, it can seem a little bit daunting at first because there's a number of tables you have to move through. You're essentially doing just 4 fairly simple steps. The first is we're going to determine just how reactive our aggregate is. remember we know it's reactive or we wouldn't be in step 2. We've determined the level of ASR risk, determine the level of prevention, and then identify what suitable preventive measures are necessary. So we're going to go through this 4-step program. Step 1, we determine aggregate reactivity. We can use either our accelerated mortar bar test or our concrete prism test to do this. And there are 4 possible outcomes. One is non-reactive, and I doubt we would be here because we don't go to step 2 unless we have a reactive aggregate. Or we can have a moderately reactive, a highly reactive, or a very highly reactive aggregate, depending on how much expansion we see in these test methods. So we can use the accelerated mortar bar test for this. It's probably preferred that you use the concrete prism test. If you have data for both tests, then and they disagree on the reactivity of the aggregate, the result for the concrete prism test would prevail. You would take that in preference. If, of course, if you test your sand and your coarse aggregate and get different amounts of reactivity, you would always proceed to the next stage assuming the higher level of reactivity. So you would always design your preventive measure based on the most reactive component, be it sand or coarse aggregate. In Table 2, the second step, we're going to determine the level of risk of ASR. And the level of risk of ASR ranges from level 1, which is no risk, to level 6, which is the highest level of risk. And the level of risk depends on our aggregate reactivity that we've already determined. And you can see we proceed from no reactive to highest, going from left to right. And it depends on the exposure condition of our structure. So we have conditions that are not conducive to ASR at the top, in other words, small concrete elements in a dry environment, through to concrete exposed to humid air, buried or immersed, which is, let's face it, most of our engineering structures. And then in the extreme case, concrete may be exposed to alkalis in service. And what we can see is that as we either go from left to right, in other words, as we increase our aggregate reactivity, we see an increase in the level of risk. But also, if we go from top to bottom, where we're increasing the amount of moisture and alkalis in service, we also increase our risk. So essentially, we're going from no risk here to the highest risk here as we move either to the right or down the table. So this defines our level of risk. In the next table, we're going to take our level of risk that we just determined from level 1, no risk, to level 6, the most level of risk, and we're going to determine the level of prevention. And the level of prevention ranges from V, which means no prevention, to double Z, which means the utmost possible prevention. And we can see that obviously the level of prevention does increase as the risk of ASR increases. We can see that here as we go from V, W, X, Y, Z, double Z. But it also increases as the classification of our structure changes. So to look at this, we're going to have to see how we classify our structure. We classify our structure based on the consequences of ASR, or you could say how acceptable it is to have some level of ASR in our structures. And we go from S1, which are non-load-bearing elements, like buildings or temporary structures. These are just examples. To S2, which are, say, sidewalks, curbs and gutters, elements with a relatively low service life level. To S3, pavements, highway barriers, etc., slightly higher level of service life typically. To S4, which are major structures. And essentially what we're saying here is that if we're building a sidewalk, we could at least accept some level of risk. Whereas if we're building a dam or a tunnel or a major bridge, we really can't accept any level of risk because the consequences are too high. Now I think this deserves some explanation. We're not saying here that sidewalks are unimportant. What we're saying is that you could accept some risk of ASR in our structure. I'll give you an example. For instance, for an S2 structure, we might end up with advice that tells us to use 20% fly ash, for instance. And, 20% fly ash is going to work 99 times out of 100. So there is some well, let's say 95 times, there is some risk of ASR. It's small. And let's face it, if we do get a little bit of cracking, 20 years on the sidewalk, it's not the end of the world. The sidewalk will probably still stay in service for as long as it's needed. If, on the other hand, we're building a major bridge on an interstate that has a service life of 100 years, 20% fly ash, yeah, it's going to work most of the time, but we really want it to work all of the time. And you'll find if you go through the procedure, you might end up having to use 35% fly ash. And that's because we really don't want to accept any level of risk at all. So let's go back to our table here. So we can see that as the risk of ASR gets more extreme, or as the consequences of ASR get worse, get more daunting, we move down in this direction here, and we have to assume higher levels of prevention to actually stop ASR from occurring. You might notice the double dagger here, and this is a case here where what we're saying here is if you have a really, really high level of risk of ASR, an extreme risk of ASR, and you're building a structure in which you can't tolerate any ASR at all, then maybe there isn't a level of prevention that's enough. Maybe you have to go back to the drawing board, select another aggregate, or something. So sometimes we can be in a position where there just isn't enough prevention available to sensibly build that structure. Okay, so once we selected our preventive measure, so remember that's level V, W, X, Y, and Z, and double Z. I'm sorry, Z or double Z. I keep forgetting to exchange my units here. Then we choose one of our preventive measures. We can go to Table 5 and select an alkali content. We could go to Table 6 to select an SEM level. If we do go to Table 6 and select an SEM level, we can go to Table 7 then and actually adjust that level of SEM based on the cement alkalis. Excuse me. And then Table 8 is for those exceptional times when we're in the double Z category, and we might want to actually both limit the alkali content of the concrete and use an SEM. Okay, so Table 5, remember we go from V, no prevention, to double Z, the most. And of course, level 5, but there is no limit on the alkali content because we don't have a reactive aggregate, or there just is no risk of ASR, and so we don't have a limit. And here's where we see our sliding scale I discussed before. Prevention level W, 5 pounds per cubic yard will be sufficient as our maximum alkali content. Get to level Y, 3 pounds for alkali. 3 pounds of alkali per cubic yard is sufficient. When we get to Z or double Z, we're forced to go to Table 8. And the reason for that is when we're in these extreme categories, we don't believe that control of the alkali content on its own is a sufficient level of prevention. And you have to use the control of alkali together with some SEM to control expansion. If we decide to use SEM, we come to Table 6. And Table 6, I don't want to spend too long on this. It seems a little bit complicated to begin with. But Table 6, let's look at fly ash. We only permit, with a prescriptive approach, we're only permitting low calcium fly ashes. And we can see for a low calcium fly ash, the level of replacement, this is a minimum level of replacement now, goes from 15 for level W to 35 for level Z. Slightly higher alkali cement, we need slightly more. If we've got a slag, we go from 25 for level W to 65 for levels Z. Silica fume depends on the alkali content available from the Portland cement. Again, an example here is what we have here is 1.8 times LBA. LBA is essentially the pounds of alkali in the concrete from the Portland cement. So if we've got about 5 pounds per cubic yard of alkali in the concrete, we're going to have to use 1.8 times out, or 9% silica fume. 1.8 times 5 is 9. The 3 times kGa, that's just the same calculation in kilograms. If we have our alkali kilograms per meter cubed instead. So you can see again, the level of silica fume is going to increase as the level of prevention increases, or of course as the amount of alkali in the system increases. After you've gone through Table 6, you can adjust the answers in Table 6 based on the cement alkalis. The data in Table 6 were basically generated from studies using moderate to high alkali cements in this range here. What we're saying is if you have a lower alkali cement here, you can actually reduce the minimum amount of SEM given in Table 6 by one prevention level. So if you're in levels Y, you can drop down to level X, for instance. On the other hand, if you've got a high alkali cement, you have to go in the other direction and increase the amount of SEM. If you have a very high alkali cement, above 1.25%, we're not sure. We don't really have the data for such systems, so we don't feel confident prescribing advice without the data to support it. Table 8 is the special levels of prevention. So what we say in Table 8 is, first of all, for level Z, we say that you can either use the SEM shown in level Z on its own, or if you want to use slightly less SEM, you can drop the level to level Y, but also control the alkali content of the concrete. If you're in level double Z, here you've got no choice, you have to use both. So if you're in double Z, you have to use the SEM in level Z and control the alkali content of the concrete. Now that might seem very extreme to you, but let's face it, if you're in double Z, you're essentially using the most reactive aggregate available and you're building a critical structure. So that's why we find ourselves in that position. So a summary of PP65, it deals with ASR and ACR as we've seen. We have prescriptive and performance alternatives for determining preventive measures. The performance approach allows the use of accelerated tests and the concrete prism test, but does recommend correlation of the two tests. And the prescriptive approach, the actual level of prevention varies with risk as defined by the reactivity of the aggregate, the nature of the concrete, and the exposure condition. I'm going to give a quick example of using this. We're going to have a quick run through. We're going to imagine we have a concrete for a bridge deck on an interstate in North Dakota. We've got accelerated mortar bar test for coarse and fine aggregate, and we've got concrete prism test for both. And the only SEM we have available in this example is low calcium fly ash with a low to moderate alkali content. So we look at our accelerated mortar bar test and we find that our fine aggregate is an R1, our coarse aggregate is an R2. In this case here, we also have concrete prism test, so we find that the actual results don't agree. We find that our fine is R0 and our coarse is R2. Well, because the concrete prism test prevails, we are going to take this result here for the coarse aggregate, and because this is a higher reactivity than the fine, we're going to use this level of reactivity. Had we not had this test information available, we would have used the results for the coarse aggregate and be designing for the higher reactivity class of R3. So we'll go to Table 2. We know it's R2, we just determined that, so we look down here. Because we're in an interstate in North Dakota, it's a bridge deck, so it's going to be exposed to moisture, of course, but it's also likely to be exposed to de-icing salts, which are probably sodium chloride and therefore alkali, so we're going to find ourselves in level 5. As we're on an interstate bridge, we're going to assume that this is an S4 category. It's a major structure. We really don't want to see any ASR. The consequences of ASR, of course, are we'll get cracking of the bridge deck, freezing and thawing will actually take over, and obviously chlorides can get down to our stills. So we really don't want to see any cracking at all during the life of the structure. So we're in S4, we're risk level 5, and of course these two meet at prevention level double Z. Here are our options, limit the alkali content of the concrete, etc. We can see here we want to limit the alkali content of the concrete. Our only option is is table 8. We can also see, because we're in double Z, we actually can't use SEM on its own either. We're going to have to go to table 8. And if we go to table 8, we actually find ourselves in this position here, where we have to both limit the alkali content to 3 pounds per cubic yard and use the SCM level as shown for level Z, which, as you can see, is 35%. So the result of this is our prescriptive solution is to use 35% fly ash and to limit the alkali contents of the cement to 3 pounds per cubic yard. Our alternative is to conduct a performance test and and actually find out exactly how much fly ash we need with this aggregate. We run either the accelerated test or the concrete prism test with various levels of fly ash and see what's the minimum level of replacement we need to control expansion. Hopefully then we could add in a safety factor and use more than the minimum decided by those test methods. Okay, what I wanted to do now in some of the time that's left to us is very quickly show you, and I hope this works, just a minute here. I got too many things open. So, okay, this might seem unduly complex, and I've got to turn my pen off first. Let's just get out of that. That's probably the easiest way. To some people, this might seem unduly complex, and one of the things we've done is we put this into a fairly simple computer program, which is currently being reviewed by Federal Highways, and hopefully will be available on the internet for download, free download fairly soon. And this is essentially just a little program that allows you to run through those things in much the same way. I'm only going to give you a fairly short example of this. So it asks questions, and it skews the font size here. You might need to get yourself a pair of reading glasses to run this. So it asks questions like, is there a proven history of satisfactory fill performance? If you press yes, it's going to tell you, well, that's okay, you can use it, but there's a certain level of risk, whatever. So you can you can either accept it and stop there. Petrographic examination, the same thing. It is, do the results of petrographic examination indicate aggregate to be potentially reactive? Let's say they don't. No. Then again, you can accept it for use, but there's a certain level of risk. So you can accept the aggregate by clicking this box here, or you can do the further testing. Is the expansion of mortar bars greater than 0.1%? Well, take my word for it. If you say no, it says accept the aggregate, but then we have to start the program again. So let's say yes, it does. Is the expansion of the concrete greater than 0.05%? And it says here, if data from this test are not available, then select yes. In other words, assume because you passed the mortar bar test, if you don't run the concrete prism test, you have to accept that your aggregate's reactive, so we'll press yes. Aggregate is alkali silica reactive, take preventive measures or reject the aggregate. So let's say we accept preventive measures. If we decide to go the performance approach, then basically what it's doing here tells us to run the prism test or the mortar bar test. It allows you to check the mortar bar test here by putting in the expansions and determining where it falls. But let's go. So that's simply all the performance test does. Let's go into prescriptive approach here. There's a little bit of a description of the prescriptive approach. Then tells you to select your aggregate reactivity. Then tells you to select your exposure conditions. So let's select your exposed to moisture and service. Tells you your risk of ASR is level 4. Tells you to actually select the classification of structure. So let's say we're building a barrier wall or something like that, pavement, continue. Tells you your level of prevention required is Y. Then gives you the option of limiting the alkali content or using SEMs. Let's take the using SEM option. Now it's asking you some questions, because to use the SEM we have to know a certain number of things. especially if we're going to be using silica fumes. So it wants to know what the alkali content of the cement is. Let's say it's 1%. Wants to know what the alkali content of the fly ash is. Let's say it's 2%. And wants to know the total cementitious materials. Let's say we've got a data of 700 pounds per cubic yard. Tick the units. And then it gives us options. Do we want a single SCM? Do we want combinations of ash and slag, ash and fume, slag and silica fume, or maybe even a quaternary blend with fly ash, slag, and silica fume? So we're going to select just a single one here, just as an example, and then it will give you your answers here. And you can obviously go back and check other options. So as I say, this is it's still in development in the sense we're still responding to reviewers' comments, but we hope to have this available, I would say, within the next few months. So we'll keep you posted on this. Okay, so I think I've finished with time enough to fill a few more questions, and hopefully Benoit's back with us too.
Okay, thank you, Dr. Thomas.
Yes, I'm here. Sorry, I had to.
Okay, Dr. Fournier is on the line as well, and we're going to go ahead and pick up again with the questions that we have. The first one is, has anyone looked at adding latex admixture to specimens made for the concrete prism test to try to reduce the amount of leaching in the test?
Not to my knowledge, no.
Same here.
Okay, next question is, are there any concerns with the elevated multi-laboratory precision allowed by ASTM C1260?
Oh, I think there's concerns with the precision of any test. You know, it certainly doesn't help the engineer where he's looking at results that are borderline around those test methods, you know, around the limits. Yeah, I think like any test, its precision is not as good as it would be, as we would like it to be. All the ASR test methods that we run have don't have great precision. I'm afraid they're not that repeatable. I mean, they do depend a lot on the ability of the laboratory to run the test properly. They depend on operator skill and precision too. So I think there's a concern. I'm not sure how we address it. Perhaps the only way to address it is to come up with simpler tests. But given the problems with the test methods that we have, I don't see them becoming any simpler. But the more complex that they become, obviously, the more potential there is for operator error, and therefore spread the decrease the repeatability of anything.
Okay, very well. The next question is, can you give an example of a carbonate aggregate that would have the potential of ACR? What is the chemical or mineral composition of a carbonate that would cause ACR?
Well, this is a question I'm going to quite happily hand over to Benoit.
Yeah, we do have a test method in CSA standards. And also it is part of the AASHTO specification, if I recall right. This test is basically consists in running an oxide content, if you like, by chemical analysis. And in that test procedure, there's a chart there where you can plot the result of calcium oxide over magnesium oxide, plot against the aluminum oxide. And on that chart, you can actually find an area where the experience has been by testing aggregates showing potential alkali carbonate reactivity, at least in Canada, that if the plot of your chemical analysis for the limestone aggregate that you have actually falls into that section, the aggregate can be considered as potentially alkali carbonate reactive. If the chemistry is such that the composition falls outside of that zone, then the material will not be considered as potentially alkali carbonate reactive, and then you can subject the material to the 1260 accelerated motor bar test or concrete prism test. Also, petrography might give you a feeling if a petrographer with some experience of ACR look at the rock. The alkali carbonate reactive limestone will have a particular texture that Mike has shown in his presentation last week, which consists in grains of dolomite disseminated in a fine grain matrix of calcite and clay minerals. That there are a number of pictures of such textures in textbooks and standards document, and if you see such type of texture through petrographic examination, that can give you an potential for alkali carbonate reactivity.
Okay, the next question is, are you aware of PP65 procedures for assessing risk and mitigation being accepted by use in commercial construction or by code bodies?
Not at this point in time. It's relatively new. I know we did discuss it in the ACI 301 committee, which is a committee for specifications. It was on the table there at one point. I'm not sure what the final decision was, but no, the specification is definitely in its infancy. I mean, it's really only been around for a year or less.
Okay, the next question is regarding the example with 35% ash, and the attendee is asking if that is on a bridge deck. He states that in members exposed to de-icer salts, like bridge decks, that fly ash is limited to 25% in order to prevent de-icer salt scaling.
Yeah. Yeah, and you know that raises a very good point. You know, that's one of the reasons why we wanted to have a sliding scale of risk. You know, you have to accept the fact that the best way to avoid ASR is to use the highest amount of with a reactive aggregate is to use the highest amount of fly ash or slide that you possibly can. But of course, there's other limitations on that. There's limitations regarding constructability, like it might just take too damn long for stuff to set up. There's problems with other durability issues, like the scaling issue as well, if you use too higher replacement levels. And that's why we try to build in as much flexibility. So that 35% is only required in the most extreme circumstances. If you're building a sidewalk, you could get away with 20% following the same specification because you can accept a slightly higher level of risk. So in that situation, I use the most severe situation, you end up with 35% fly ash. And don't forget, again, that is for the most extreme possibility, you know, where you've got, as I say, you're using the most highly reactive aggregate known to man, building a major structure, and you're going to throw salt on it. And you may well decide that 35% isn't acceptable because of other considerations like the limit on salt scaling, and then the option is, well, you're going to have to use a less reactive aggregate to find yourself in a lower category. So, you know, we're not saying that by using the standard you can build concrete structures with whatever aggregates you like. You can't. You can under certain circumstances, but those circumstances may not suit other construction considerations. And I think that's a perfect example. If you want to use 35% fly ash where you're throwing de-icing salts on, there's a risk of de-icing salt scaling. You know, maybe you have to look for another option in that situation. Maybe you have to look at a ternary blend, or maybe, as I say, probably in that situation, you would have to look at using. Don't forget that is for, you'd have to look at using a moderately reactive aggregate instead of a highly reactive aggregate. So definitely, it's a good question. That, you know, I think it highlights that sort of need to consider other possibilities. You know, you have to consider other construction issues as well.
Okay, fair enough. The next question is about the AASHTO program. Do you enter the total alkali or available alkali content for the fly ash?
It's the total. And the reason for that is that the available alkali content that used to be an option in C618 is kind of a misnomer. It's only the available alkali content. It only measures the alkali that's available to that test method. And the amount of alkali that's available depends on the test method that you use and the conditions. That essentially all of the alkali that's in fly ash can be considered to be available eventually under the right circumstances. So a decision was made to use the total. That's usually the easiest one to measure as well. You can easily obtain it from X-ray fluorescence when you're doing a standard chemical analysis. But it is the total. But I think there's a good rationale for why that's the case.
Okay. The next question is, could you discuss pop-outs? Is this condition truly ASR since it happens so quickly in cases, or is it more of a finishing issue with trapping in bleed water?
I think it depends on the pop-out. Many pop-outs are due to freeze thaw damage, so they're nothing to do with an alkali-silica reaction. There are some other types of pop-outs which we see in certain parts of the country where it's just we have ASR limited to the surface of the concrete, to the surface layer of the concrete. And in my experience, these occurs in situations where concrete's placed in a relatively wet condition on a day where there's a lot of evaporation, and there's a lot of bleeding as well. So the bleed water rises to the surface, it evaporates, it brings lots of alkali with it, and you can significantly concentrate the alkali at the surface, very significantly. Some people have shown almost a 10-fold increase very close to the surface, and you can get pop-outs occurring there because of the very enhanced alkali content at that surface. I think under those circumstances, yes, that is ASR. It's not a very frequent phenomenon at all, as far as I know. It's only actually confined to a few sort of specific locations where they have certain aggregates. But on those situations, it is an ASR problem. But don't forget, pop-outs can be caused by things like frost damage. It can even be caused by things like iron sulfides in the aggregate close to the surface as well. So there are different causes of pop-outs, but those ones that occur very quickly in flat work, yeah, I think that's very rapid ASR that occurs.
Okay, the next question is, do steel slag and air-cooled slag sands typically have low expansion properties or not?
I don't think I can really comment on that. I've seen problems with what was the other one? Air-cooled sands?
Steel slag and air-cooled slag sands.
Okay, so by air-cooled slag, I'm going to assume that they mean air-cooled iron blast furnace slag. I'm not aware specifically of problems related to ASR with those types of aggregates, but there could be other durability-related problems. I'd have to say I'm not really aware of that much testing on such aggregates for ASR. I have tested some iron blast furnace aggregates myself, and the aggregates I tested were not alkali silica reactive. But there obviously is a potential for some to be. I mean, they are silicious in nature. It depends on the cooling conditions. It is possible that you could form reactive silica during the cooling process. So I wouldn't rule it out. But in my experience, the iron-cooled blast furnace, the air-cooled iron blast furnace slag I tested, I haven't seen reactivity. Steel slag sands, I really can't comment. Benoit, I don't know yet.
No, I have no experience with testing these types of materials.
Okay. The next question is, on the AMBT versus CPT plot, couldn't the upper range for applicability of the AMBT test for mitigation effectiveness be eliminated? It seems as if mitigation measures would be effective for an aggregate with a high AMBT expansion and a relatively low CPT expansion if the mitigation measure passes the AMBT test.
Yeah, that point is frequently raised. You know, can you still see my screen? Is it still visible?
Yes, you're still on.
Oh, okay, okay. So I think what we're talking about here is, I don't seem to have the, I don't, there we go. Let me just click on this pen here. We're talking about, I think, results that maybe fall in this range here. So we're outside of this, but we're getting more expansion of accelerated motor bar test than we are in the concrete prism test. So it's a fair argument could be made that it's conservative doing this, because if you end up having to put in SEMs to control in the accelerated motor bar test, you're probably going to end up putting more than you would do in the concrete prism test. So you're definitely conservative and you're on this side here. However, I really believe that the trouble with having an aggregate hazy is you're still getting the wrong result. It may not be as wrong as it could be. I know that doesn't sound right, but you still are getting the wrong result. The accelerated motor bar test is telling you something that it shouldn't tell you. And, you know, to some extent, even though using more SEM is more conservative than you're going to end up using more SEM than you need, which is conservative, I believe that it's still bad engineering. You know, if you end up using more SEM than you actually need, you run into the issues of perhaps you create some other durability problems. You also could create a position where somebody maybe decides not to use that aggregate. You know, the result tells them they need 35% fly ash. They don't want to use 35%, so they don't use it. And yet, if they had the right result, they could have used it. So I don't know. I think a wrong answer is a wrong answer, no matter how conservative it is. But I do see the argument that at least we're conservative in that side of the graph.
Okay, thank you for that. Looks like we've covered the questions that have been submitted today. We have a few minutes to spare, so I want to go back to and try to cover at least a couple of the questions that were left over from last week. One of those is ASR visual distinction over ACR, ASR visual distinction over ACR would be wet looking, crack which is actually gel material.
No, I wouldn't say that was reliably diagnostic. I mean, it is true that you don't get it as much or very little exudation activity around alkali carbon reactive cracks, or even none, but you can also get alkali silica reactive aggregates that also give you a little gel exudation. So in my opinion, and I'll ask Benoit to give his opinion in a second, but in my opinion, if you've got matte cracking on concrete, if you want to determine this ASR or ACR, you have to take a call.
Yeah, this is certainly the safest way for sure. I agree with you, Mike. Yeah.
Okay, and what is the approximate time frame where we start to see ASR or ACR formation?
That depends on so many factors. It's just,
yeah.
You know, it obviously depends on the composition of the concrete, the reactivity of the aggregate, and it depends on the alkali content in there too. And it's also going to depend on the moisture availability, and of course it's going to depend on the temperature of the environment. You know, we do quite a lot of work where we put parallel specimens on our sites up in Canada, and you know, our colleague Kevin puts the same concrete mix on his site down in Texas, and you know, there can be a factor of 6 times difference in the time it takes for expansion to occur because of the differences in climate. And that's not even allowing for any differences in composition of the concrete. So, you know, I would say with ASR, I've seen evidence of it occurring as early as 1 to 2 years. on Kevin's exposure site can be as early as 3 to 6 months, but that's, you know, really making the concrete as reactive as you possibly can. So, but in field structures, I've seen it as early as 1 to 2 years, and I've seen it appear as late as more than 10 years. You know, out in the west of Canada, there's been reported cases of ASR where the cracking hasn't really shown itself for 12 to 15 years or something. So that's an open book. It's hard to give an answer to that.
Okay, we'll go for one more here, and then we'll wrap it up for today. And this, you may have covered some of this in today's presentation, but again, this question was from last week. It's, can you please comment on ASR in concrete containing fly ash?
That's an open-ended question. Well, hopefully the concrete contains a sufficient level of the appropriate ash. We wouldn't have ASR. I'm not sure what the person means. For sure, ASR can happen in fly ash concrete. Again, if the fly ash is not there in sufficient quantity, or it's, you know, or the composition of the fly ash doesn't make it suitable for ASR. So ASR has occurred in fly ash concrete. We can make it occur in the laboratory. However, fly ash can be used to control ASR provided it's used in sufficient quantity. That's really my only comment, I think, to the question as it's posed.
Okay, thank you, Dr. Thomas and Dr. Fournier, for taking those questions and for the presentation today. Thank you for those attending, and once again, remember that the final session is scheduled for next Wednesday, the 20th. It will also be at 1 p.m. Eastern Standard Time. And again, just watch your email inbox. You'll be receiving information about that with the links to click. Thanks again to everyone, and have a great day.